Hello, everyone. Thanks very much for joining us for today's media teleconference. I'm Elise Fisher with NASA's Office of Communications, and today we're here to discuss an update on the agency's Hubble Space Telescope operations. So with us on the line to provide that update and answer your questions, we have Mark Clampin, Director of the Astrophysics Division in the Science Mission Directorate at NASA headquarters, and we have Patrick Krause, our Hubble Project Manager at NASA's Goddard Space Flight Center. So we're going to hear briefly from each of them, and then we will have the opportunity to take your questions for those media who are listening on the phone line. So when we get to that point, you'll be able to ask a question by pressing *1. But first, I will turn over to Mark Clampin. Go ahead, Mark.
Thank you, Elise. So my name is Mark Clampin. I'm the Director of Astrophysics, and I'm going to talk to you about Hubble. So Hubble has been observing the universe for more than 3 decades now, and will continue to do so for years to come and benefit the science community. It's already more than doubled its life expectancy. However, over the last 6 months, one of Hubble's gyroscopes, or gyros as we call them, has increasingly returned faulty readings, and these, of course, are spacecraft to enter its safe mode multiple times. So just to explain what gyros are, Hubble's gyros are part of the system that determines and controls the direction that the telescope is pointed. So as we slew to a new target, they measure the telescope's slew rates, or the rate at which it moves to the next pointing so that we arrive at the right place for the next science observation. Most recently, the telescope went into safe mode on May 24th, again due to issues with this same gyro. So after completing a series of tests and carefully considering our options, we have made the decision that we will transition Hubble to operate using only one of its 3 remaining gyros. Operationally, we believe this is our best approach to support Hubble's science through this decade and into the next, since most of the observations it takes will be completely unaffected by this change. One gyro mode actually returns Hubble to consistent science operations, which is important, and it allows us to keep another gyro working, although we will maintain it powered up in reserve for potential future use. So now I'll turn it over to Pat Krause, the Hubble Project Manager, who will share more about the one gyro operations and what this means. Pat.
Thanks, Mark. This is Pat. So as Mark mentioned, for months, this particular gyro, Gyro 3, has experienced repeated saturation events. So essentially, the gyro outputs what it thinks is a maximum slew rate that it can potentially put out, which is faulty and causes this. It thinks the spacecraft is slewing at the maximum rate, and that in turn causes us to go into safe hold. And the team has repeatedly been able to take steps to return the gyro to normal readings, but the results have proved only to be temporary, and the problem reappears and has been reappearing more frequently. As was mentioned, the last time we went into safe hold was back on May 24th, and our attempts to pause the gyro to restore normal readings at that time proved to be unsuccessful. So our team now is developing the process and pursuing the process to transition to one gyro operations. Our team first developed a plan for one gyro operations over 20 years ago, and it is the best mode to go forward to prolong Hubble's life. And as Mark said, to consistently return us to science operations. And although Hubble can continue science operations in one gyro mode, there are some limitations in comparison to our normal 3 gyro mode. It will take us more time to slew from one target attitude to the next, and to be able to lock on to that science target. And so that will lead to lower efficiency for scheduling science observations. We currently schedule about 85 orbits a week, and we expect in one gyro science mode to be able to schedule about 74 orbits a week, so about 12% reduction in scheduling efficiency. In addition, we won't have quite as much flexibility as to where we can observe on the sky at any one time, but over the course of a year, we will have the full sky available to us to observe, and we will be unable to track moving objects that are closer than Mars, although those targets have been rare targets for Hubble over the years. We do expect the transition to take us a little bit of time, and so we're looking forward to having science observations again beginning in about mid-June.
All right, thank you both very much. So we will now go ahead and begin taking questions. So again, if you are on the phone lines and you'd like to get into the queue to ask a question, you can do that by pressing *1. And when you ask your question, if you know which speaker you'd like to direct it to, please do let us know. So now we'll go ahead and take our first question. This will be from Bill Harwood with CBS News.
Yes, thank you very much, folks. I'm not sure who this is for, but just in general, when you guys have analyzed statistically the flight history of the 6 gyros that were installed on the last servicing mission, what sort of numbers do you get to be able to predict lifetime on the 2 that are left? And if you go to and in one gyro mode, since you're keeping one in reserve, I'm just wondering. Well, I don't know. I mean, just that. How much do you think you can get out of these guys based on the performance of the other 4? Thanks.
Thank you, Bill. Pat, would you like to take that first question?
Yeah, I'll take that on. So of the 6 gyros that were installed in service mission 4, 3 of them were what we called standard flex lead gyros, and 3 were what we called enhanced flex lead gyros. The enhancement was that they were able to sputter silver plating on all the flex leads to prevent corrosion. Corrosion was a known failure mechanism for the standard flex lead gyros, and in fact, the 3 gyros that have failed since service mission 4 have all been standard flex lead gyros. And the standard flex lead gyros that have failed typically have run on average about 42,000 hours. What we've seen so far with these enhanced flex lead gyros is that the average of the 3, they've ran over 101,000 hours through May. And also by removing that corrosion failure mechanism, our assessment has been that we could anticipate that these enhanced flex lead gyros could operate on the order of 5 times longer than the standard gyros, based on a reliability assessment that we worked with in NASA Engineering and Safety Center.
Great, thank you, Pat. Our next question here is from Jeff Faust with Space News. Go ahead, Jeff.
Good afternoon. A question probably for Mark. How does this change to single gyro operations affect the operations paradigm change review that you announced back in March to look at ways to reduce the cost of operations of both Hubble and Chandra now that you have this single gyro mode to deal with? Thanks.
So thank you for the question, Jeff. I don't think it changes the outcome of that review. I mean, as you heard already, we will continue to operate Hubble. There are some limitations that Pat Krause outlined, but they're not what I would call serious impediments to continuing science operations. So, we will continue to operate Hubble. The operations paradigm change review has just completed, and we've received the panel's findings. Right now, we're in the process of reviewing them, and we plan to share an update later this summer with how we're going to move forward based on the recommendations of that review.
Okay. Thank you, Mark. We'll take our next question now from Jim Siegel with Florida Media Now.
Thank you. Thanks for taking my question, and hi, everybody. My name's Jim Siegel, and I've been wondering about what the annual operating cost of Hubble is, both before all of this took place about the gyros, and then starting in June or whatever it was. What would be the annual operating cost then? Thank you.
Thank you, Jim. Mark, would you like to take that?
So Jim, I can give you not a precise answer, but a pretty close answer. So last year in FY23, the annual operating cost for Hubble was about $95 million. I want to just emphasize that that breaks down between the cost of operations of the mission, but also the grants that go to the science community, and the Space Telescope, who operate Hubble, also run the Hubble Fellows Program, which is broken into 3 parts. So the cost of that program is also included in that number.
Thank you, Mark. Our next question is from Marcia Dunn with the Associate Press.
Yes, hi. As much as everyone loves Hubble, would you consider this a sign of a point of no return? Would you consider Hubble on its last leg at this point with only 2 gyroscopes now remaining? And what's the latest on the Hubble mission proposed by Jared Isaacman? Is this new breakdown going to give more support for mounting such a mission? Thanks.
Thank you, Marcia. So maybe, Pat, would you like to take the first part of that question about, Hubble's future from here, and then Mark can follow up and address the question about the reboot proposal?
Sure. So our reliability assessment for Hubble conclude that we still believe there's very high reliability and likelihood that we can operate Hubble very successfully, doing groundbreaking science through the rest of the 20s and into the 2030s. We updated our reliability assessments for the gyros, assuming that this gyro is no longer useful to us, and we still come to a conclusion that greater than 70% probability of operating at least one gyro through 2035. We currently have 4 instruments that have been robust and highly productive, and we certainly see that reliability is expected to remain very high. So we do not see Hubble as being on its last legs, and we do think it's a very capable observatory, and we're poised to do exciting science with the other observatories on orbit and those that will join us on orbit.
Thank you, Pat. And Mark, if you want to take the second part of that question.
Sure. So the second part was really addressing the question of reboosting Hubble to a higher orbit. And our position right now is that after exploring the current commercial capabilities, we are not going to pursue a reboost right now. Now, I want to say that we greatly appreciate the in-depth analysis conducted by the NASA team, SpaceX, and Polaris program, and our other potential partners, and it's certainly given us better insight into the considerations for developing a future commercial reboost mission. But our assessment also raised a number of considerations, including potential risks such as premature loss of science and some technology challenges. So while the reboost is an option for the future, we believe we need to do some additional work to determine whether the long-term science return will outweigh the short-term science risk. So I just want to emphasize again that even without the reboost, we still expect Hubble to continue producing science through the rest of this decade and into the next.
Thank you, Mark. We'll take our next question from Eric Berger with Ars Technica. Go ahead, Eric.
Hi, thanks very much. Just to follow up a little bit on what Marcia said, this is a question for Mark, I think. My understanding is that there was a NASA SpaceX Hubble enhancement study done about a year ago that recommended you proceed with the concept. So, given what you just said, could you talk a little bit about why NASA decided to not proceed with that? And then there were some options in that mission, like addition of star trackers, that might have mitigated some of the issues of going down to a single gyro. Is that something you'd still be interested in, given that you're now going down to operations with a single gyro? Thanks.
So I think the first point to make is that it was not a go, no-go kind of study. It was a feasibility study to help us understand some of the issues and challenges that we might have to face were we to do such a study. And as I said, we are very grateful to SpaceX and Polaris for working with us on that question. But there was never a sort of recommendation to go forward. There were options such as the possibility of doing enhancements by adding gyros to the outside of the telescope, but they were really just notional concepts. We never even got to the point of actually looking at what that would look like and how we would do that. So, as I said before, for the time being, we are stepping back and we're going to be taking a more detailed look at some of these risks that we have to understand, and also what the overall requirements for such an enhancement would be if we were to go forward.
Thank you, Mark. We can take our next question from Marina Corin with The Atlantic.
Hi, Marina Corin with The Atlantic. A question for Pat, I think. Someone on the Hubble team once told me that that a one gyro scenario would possibly involve Hubble using some of Earth's magnetic field to orient itself. Is that something you'll be doing now? And if so, how would that work? And for Mark, just to follow up on Eric's question, so you're saying that you want to take a more detailed look at some of the potential risks of a servicing mission. What are for you the biggest risks of a potential commercial servicing mission? Thanks.
Great, thanks, Marina. So, Pat, would you like to take that first part of the question, and then we'll go to Mark?
Yes, I will. So you're correct. So in our one gyro science mode, it's effectively made up of 3 different modes that we use in succession. So as we leave one target to go to a new science target, we go to what we call our magnetic sensing one gyro mode. And in that mode, we use the core sun sensors and information from the magnetometers that are on board the spacecraft. We have a model for what the magnetic field of the Earth should be relative to where we are in orbit. And by using that information, we're able to know kind of what our attitude is, and also what the magnetic sensor essentially pushes against the Earth's magnetic field to help reduce the attitude errors. You're going from one starting attitude to a final attitude. So we do that magnetic and one gyro for the transition. As we get closer to the target within the field of view of our fixed head star trackers, we switch over to the fixed head star trackers and the gyroscope to take out some additional error and to reduce the rates on the spacecraft as we're getting to the next science target. And when those are sufficiently small, the fixed head star tracker control will hand over to the fine guidance sensor control. And that gets us at the milliarc second pointing level.
Thank you, Pat. And Mark, if you'd like to address the second question.
Sure. So the question asked me what might some of the risks that we were going to be looking at look like. So I want to just remind people, the last time we went to Hubble was on the space shuttle, and it was, quite a long time ago. So when we concluded the study, one of the sort of key pieces of information that we took away is that, yes, it will be feasible to conduct rendezvous docking and undocking, but in order to do this for the first time, a new docking procedure with a new spacecraft and a new destination, there were obviously going to be risks that needed to be assessed and properly understood. And, there's a number of different layers to that risk, right? I mean, there's obvious ones like potentially you could contaminate the mirror of the telescope because it's an ultraviolet optical telescope, and even small amounts of volatiles can get on the mirror and cause loss of sensitivity. And then there's the layers associated with the new space vehicle and with a new destination, which is Hubble, which is something that hasn't been done for a long time. And of course, Hubble is an old spacecraft now, so a lot of the people who are very involved in the early servicing mission have retired, and there's a lot of work we would have to do to get back up to speed on how to do that.
Thank you, Mark. Our next question in the queue is from Gina Sansari with ABC News.
I'm not sure who wants to take this, but despite the diminished capacity, can you point to a recent image or discovery by Hubble that makes you want to just cheer it on?
So I'm going to just sort of point out that we are routinely putting out new images from Hubble. But what I really want to do is just point to the approved proposals for the current cycle of observations. And I think the reason we, cheer it on is because it is performing such a breadth of great science that we want to keep doing, such as studying objects in our solar system, studying the atmospheres of exoplanets. It provides a wonderful complement to Webb, because with Hubble we can do optical observations of exoplanet atmospheres, and that tells us a lot about hazes in the upper atmospheres of these planets. And again, it also provides us with valuable insights into the formation and evolution of galaxies. If you just cast your eyes across the range of different programs that are being done during this current cycle, you'll see that it's just producing a range of new science observations across different fields, as we expect our astrophysics observatories to do.
Thank you, Mark. Our next question is from Nell Greenfield-Boyce with NPR.
Hi, thanks for having this update. Could you explain why NASA isn't just going ahead and making plans for at least some minimal reboost mission through traditional procurement, with partners in the space industry, asking who would be interested in such a thing? Because, at some point, unless you're going to let this just fall into the atmosphere uncontrolled, something is going to have to be attached to Hubble. And it just seems like, the way things go and how long it takes, I know you've got some time, but not forever. And this is iconic, right? I mean, Hubble is the most popular science instrument possibly in history. And it just seems strange to me that everything's just kind of being pushed down the road again and again. At some point, it's going to end. And why not invest, a few tens of millions of dollars to just get ready for that day?
Thank you, Nell. Mark, go ahead.
So, Mel, I guess the first point I'd like to make is that, our latest predictions that the earliest Hubble would re-enter the Earth's atmosphere is the mid-2030s. So we are not, going to be seeing it come down in the next couple of years. And yes, this is space. Space is hard, and it takes time to plan and figure out how you're going to do these kind of programs, whether it's a reboost or adding something to the telescope. I also want to just emphasize that one of my jobs as the Director of Astrophysics is to implement the recommendations of the National Academy's Decadal Survey, and I have a set of priorities that have been laid down by the Astro 2021 Decadal Survey, and those form my priorities. So, as I look at my budget, and, it's a relatively flat budget right now, I have to prioritize what I do first. But that's not to say that we are not looking. As you've heard, we conducted a feasibility study, and we decided now that we have a lot of material to process and think about, we can step back, take a serious look at the best way to reboost Hubble going forward, and we will do that.
Thank you, Mark. Our next question in the queue is from Lee Billings with Scientific American. Go ahead, Lee.
Hey there. Quick question. I'm not sure for who, because most of my other ones have already been asked. But Pat, you mentioned earlier that you're typically scheduling 85 orbits for Hubble. It's going to be about 74 now, 12% reduction. In one of the links that was included in the materials for this announcement, there was a statement that said, it was the one that was unpacking the specifics of the one gyro operation. There was a statement that said the observatory could possibly lose up to 20 to 25% of its productivity. 20 to 25% of its productivity. I don't know what that means. What does that mean? What goes into that number? Those numbers?
Thanks, Lee. Pat, would you like to take that?
Yes, I'll take that. So the biggest part that goes into that is the efficiency. So we talked about losing about 12% efficiency of what's actually available to us to schedule. The rest of that number kind of comes out of a heuristic assessment of the types of science that we might not be able to do. For instance, because of the magnetic control going from one target to the next, we have more error in that process, and we have to expand the protection angles for the solar exclusion. So typically, we would currently run with a 54-degree angle we have to avoid the sun. We'll expand that to 60 degrees in one gyro science, and that reduces how much of the sky is available at any one time. So that will impact some of the types of science programs that can be scheduled. The nature of how they would like to repeat observations on a certain cadence may be impacted. Also, when Hubble it tries to react to some very time-dependent type observations, it could be that the part of the sky that we need to observe just simply won't be available to us, and so that's an impact. And there's other types of scenarios like that different types of observing techniques that we've developed over the years may not be available to us, and so certain types of science may not be available to us. And so it was an assessment that the team made some number of years ago when we were giving some consideration to whether we should preemptively go to one gyro science. And we concluded at that time that we were most productive in three gyro science and that we were better off to continue in three gyro science as long as possible.
Great, thanks, Pat. We can take our next question from Marcia Smith with spacepolicyonline.com.
Thanks so much. My first question is, what is it exactly that failed on the gyro, and are these gyros used on other existing space telescopes, or are they planned for any of the future ones? So basically, what's gone wrong with this one, and what have you learned for the future? And the other question is just, looking at Hubble and Chandra, because you were looking at whether or not you should continue the funding for Chandra because it was becoming more expensive to operate, even though it is also producing really good science. So could you just talk for a minute about how you look at Hubble and Chandra in this context of how much it costs to operate versus the science you're getting out of it?
Thank you, Marcia. So let's go to Pat for the first question about the gyros specifically, and then we'll go to Mark.
Okay, so the gyros specifically, these are mechanical gyros that are, in my understanding, are no longer in production. Certainly the ones that were made for Hubble have not been in production for a number of years. And so there's no real risk of future missions using these types of gyros and having issues. The issue with this particular gyro is that we believe it's a fault in the pulse rebalance loop. That's sort of a fancy phrase, I guess, for there's a float inside the gyro that sits in a fluid, and there's the force to kind of restore that float, and the amount of that force it takes to restore it back to sort of a center point is how you measure precisely the rate that the spacecraft is undergoing. That float it appears that it's being pushed all the way to the extreme. It could be either electronic issue or a mechanical issue. We postulated both, that it could be corrosion built up in the system, and then there's also some evidence that it's a temporary electronic issue. One of our previous attempts to restore the gyro to good performance was a power cycle of the gyro, a full power cycle that allowed it to sort of re-clear any issues that were built up in the electronics, and that seemed to be very successful for us. But we ultimately then only ran for about 10 days before some other problems, the same sort of problems, reemerged. So it certainly wasn't simply a electronic issue.
Thank you, Pat. And we can go to Mark for the question on Hubble and Chandra.
So, Marcia, as you know, we are operating in a very challenging budget environment right now, and that ultimately means we need to make difficult decisions. And as I already said, my priority is to maintain both a balanced astrophysics portfolio, make sure that I am addressing and moving forward on the National Academy's decadal survey recommendations, And so as we looked at our budget as a whole, we decided that maybe it was time that we tried to reduce the operating cost of both Chandra and Hubble, and that is why we held this operating paradigm change review. That does not mean we're going to stop taking science. The whole point of this review was to figure out how we could continue science operations, but continue them at a lower price point than we have been operating.
Thank you, Mark. Our next question is from Douglas Gorman with Payload Space.
Yeah, hi. Thanks for having the call today. Sorry to bring it back to this kind of topic, but I was wondering when you were doing the feasibility study for having commercial input on boost or repairing some of these gyros, what are some of the criteria that you look for? Basically, what would make NASA comfortable with having a commercial partner to help repair Hubble or boost it in the future? Thank you.
So I don't think I want to get into the details of the feasibility study because that's obviously proprietary. But the kind of criteria we're looking for is just to make sure that we really understood how to do the docking, the undocking, operations in the vicinity of the telescope, and basically put together a package that would allow us to feel comfortable going forward with the reboost.
Thank you, Mark. Our next question in the queue here is from Ian Atkinson with NASASpaceflight.com.
Hi, Ian Atkinson, NASASpaceflight.com. Thank you for taking my questions and for the information we got today. So I have a question that I think would be best for for Mark, and then a follow-up for Patrick. So given the decreased performance of Hubble, like on the gyroscopic operations, and with some computer issues we've seen in the past, have any priorities changed for the Habitable Worlds Observatory, which seems to be the only Hubble successor on the horizon right now?
So let me address this in the following way. First of all, I think when you look at our portfolio, it's a broad range of missions with different capabilities. There is overlap between, a slight overlap in the near infrared between Hubble and Webb. And then for the future mission, the Habitable Worlds Observatory, we have always said that this mission has, as the National Academy Decadal Survey recommended, two primary science goals. One is to survey the first or nearby first couple of 100 stars to look for habitable planets that might be able to be subsequently characterized to look for evidence of life. And the second one is to conduct a general astrophysics program. And the Decadal were very clear that they saw ultraviolet as a really interesting wavelength region for the habitable worlds. My expectation is that it will be a UV optical telescope. So we are moving forwards with our START and the working groups that operate underneath the START to understand the science trades for the habitable worlds and where it can take over from Hubble.
Great, thank you. Our next question is from David Curley with Full Throttle. David, are you still on the line?
Yes, sorry. Apologize. Thanks, Elise. Pat, I think I hear you say you're not sure whether it's computer/electronic versus physical on what's caused this gyro to have problems. And Pat, it sounds to me like somebody mentioned earlier, this is kind of a project that Americans fell in love with, that you're starting to tell us that we may have to get ready to separate from this love. Thank you. Hopefully, I'm telling you not to worry about separating from us anytime soon. I suppose all good things come to an end at some time. Right now, we know that our orbit lifetime is expected to last into the mid-2030s, and we expect that our major subsystems on the spacecraft that we rely on to be productive in science are also expected to last into the mid-2030s. Gyros 4 and 6 are the longest running gyros in the history of the program by far, and they have shown very solid performance. Gyro 3, to be frank, has always performed a little bit out of family on orbit. We did remove Gyro 3 from the control loop in 2011 because of performance issues. Then it was just better to move on to a different set of gyros and then come back to it. And then so in 2018, we came back to it following the failure of the last standard flex lead gyro, and we immediately saw some issues with this gyro on startup that it took us a little while to resolve. And frankly, it's been an ongoing work since 2018 on the operations team to learn to live with this gyro and make the best of it and keep Hubble very productive despite that.
Thank you, Pat. We can take a couple more questions here. Our next one is from Mike Wall with space.com.
Thank you, guys. Just a quick clarification. Did I understand right? Are the kind of two remaining gyros that are healthy of the enhanced type? And can somebody just clarify? Like, I know that their expected operational life was put into hours, but could you simplify that maybe into just years of operational life? Kind of each of those is expected to have for the future. Thank you.
Thank you, Mike. Pat, would you like to take both of those?
Yeah, I'll take that. So essentially, Gyro 4 has been operating since Thursday Mission 4, and it had hours on it during the test program. So it has had over 16 years worth of hours, which is about 140. I think we're around 142,000 hours of operations on that gyro. We're about to pass 90,000 hours on Gyro 6. So that's about 11 years, I think, off the top of my head, of hours of operations years of operations on that gyro. Again, when we looked at the failure mechanisms and we removed the likelihood of failure due to corrosion as sort of a wear out process for the gyros, and we simply look at random failure, the probability analysis there suggests that we should have a 70% probability of having at least one of these gyros available to us still in 2035. And that assumes we're operating them, having them powered all that time. The other statement that I guess we made was that by removing that corrosion factor, a materials expert on our team a number of years ago had stated that where the standard flex lead gyros had a lifetime on the order of 50,000 hours, he expected we should be able to see 5 times that for these enhanced flex lead gyros. 50,000 hours is about 6 years.
All right, thank you, Pat. Our next question is from Jeff Faust with Space News.
Hi, quick follow-up for Pat. You've mentioned that there was a small fraction of Hubble observations done in the past of moving objects closer to Mars that it will not be able to do now in single gyro mode. Do you have a rough estimate based on the history of recent observing cycles, what fraction of observations Hubble had done in the past it will not be able to do in the single gyro mode?
Thank you, Jeff. Pat, would you like to jump in?
Well, I think of this moving target variety, I think we're talking about something on the order of 1% or less. We have rarely observed the moon, for instance, and a handful of times observed Venus. We have not offered Venus as a target since, I think, 2019, when we expanded the sound exclusion angle from 50 degrees to 54 degrees. In fact, due to the performance of Gyro 3 and its impact on our potential impact it could have on our attitude. So I think, I think it's a collection of different types of observations that kind of are in that 1% impact level. That when you pull them all together, along with the impact on our ability on the efficiency, and again, just the timing of what objects are available to us at any given time that we can observe, that's where we start to get an overall impact on productivity. To be frank, I mean, I think we're going to, anytime you switch to a different control approach, different control algorithms, we're going to learn as we go forward. And I suspect the team will make adjustments that will certainly see improvements over the types of efficiencies that we're forecasting. But I think we'll be conservative at first and we'll expect to see some improvements as we move forward.
Thank you. Our next question is from Michael Greshko with Science Magazine.
Software company.
Hi, thanks so much for taking my question. Just to follow up on some of that, there was a 2016 report prepared by researchers at the Space Telescope Science Institute talking about some of the possible reduction in observations going into one gyro mode. The estimate was that it would represent a loss of about 25% of Hubble's scientific productivity. As you noted, no observations of Venus or the Moon, struggling to track asteroids within the orbit of Mars, transients, less ability to look at those, exoplanet atmospheric spectra, and then also less overlap between Hubble's field of regard and that of the James Webb Space Telescope. Could you, number one, if you're familiar with this 25% number, like how valid is that right now? And number two, could you talk a little bit about some of the other potential effects going to one gyro mode, including using Hubble simultaneously with other instruments?
So I am not familiar with the 25% number. I will say that most of the impacts you identified are certainly true. I mean, Pat has already discussed some of them. The reduced field of regard does mean it's harder to do observations of time domain science. But even with those limitations, Hubble is still doing a very broad range of science observations. So I don't personally see this as a major restriction on its ability to do important science.
Great. Thank you, Mark. All right, well, that is all the time that we have for questions today. So thank you very much again to our speakers and to everyone who joined us to listen on the line. If you did have a question that we weren't able to get to, please do reach out to us, and NASA's media team will be happy to help. And if you'd like to learn more about the Hubble mission and its more than 3 decades of scientific discovery, you can visit nasa.gov/Hubble.